Content of the talk is the following. First, we will describe the experimental setup. Then we briefly describe our previous work. Then we analyze the results and finally a conclusion. The experimental setup for the non-vibrating granular system is as follows. The system consists of an ensemble of magnetic particles that lies over a flat horizontal plate in the middle of the Helmholtz coils arrangement. In the vertical direction is applied a magnetic field that has two components. A constant magnetic field that makes particle has an effective repulsive interaction, and an alternating component of the field that makes particle move randomly over the surface. Each particle has a permanent dipolar moment. This moment tries to be aligned in the direction of the magnetic field. When the magnetic field reverses direction, the dipolar magnetic moment tries to be aligned with the new direction of the magnetic field. Then the particle rotates. As particle rotate, it rolls over the surface, making a linear trajectory. When the magnetic field reverses direction again, new impulses act over the magnetic particle, making it continue rolling in the same direction or could change randomly of direction. The final result is a random trajectory. Each particle takes energy from the magnetic field and converted it into kinetic energy. Thus, this is an example of active matter. This active matter can be controlled, but can be controlled by the frequency and the magnetic field amplitude. Of course, the phenomena also depends on the inertia of the particles and the friction between the particles and the surface. In the past, we had used this system to study phenomena such as glass transition and crystallization. In a previous work closely related to the current one, we studied a system where the magnetic particles are used as a thermal bath for ellipsoidal particles that are over the magnetic particles. The ellipsoidal particles are making of paper and lies over the magnetic particles. They move because of the random kits beneath from its surface. In the past, we had studied this system using mean square displacement, and we have shown that at long time, the motion of the ellipsoidal particles are diffusive in all the conditions, even though the motion of the thermal bath are not diffusive in all conditions. The particle in the thermal bath show diffusive motion only at high effective temperature. At lower effective temperature, the motion becomes an arrested one. In other previous work, we studied the Fourier spectra, the Fourier power spectra of the time series in the particle positions. In both cases, from particle in the thermal bath and particle and the ellipsoidal particles. In the case of the thermal bath, we have shown that the beta exponent, which measures the strength of the long-range interaction, and this beta value goes from a high values of 2.45 to almost 0, showing that the motion of the particle in the bath is diffusive only at high effective temperature. At lower effective temperature, the motion becomes subdiffusive and arrested. On another hand, the motion of the ellipsoidal particle are always diffusive, even though the effective temperature is low. Now we present an extended study showing different conditions of the thermal bath, and we study the motion of the ellipsoidal particle. Here we show a comparison of a video where the thermal bath has different effective and repulsive interaction. The value of V sub C is different. In the first case, V sub C is approximately 33 Gauss, and in the second case, V sub C is 0 Gauss. The effective temperature is high in both cases. We can observe the motion is faster in the case where the effective interaction between the particles in the thermal bath is higher. Here we present a comparison of the motion of the ellipsoidal particles under different effective temperature in the thermal bath. As we expect, the motion at higher effective temperature in the thermal bath makes the motion of the ellipsoidal particle is faster than the case where the effective temperature of the thermal bath is lower. Here we present the Fourier power spectra for the component X in the motion of the ellipsoidal particles. In this case, we present two graphs of two particles with different aspect ratio, and each curve means a different constant magnetic field. In both cases, the effective temperature is high. As we can see, the beta value, which measures the intensity of the long correlation interaction between the particle, this value is close to the value of 2, showing that the motion in these cases are Brownian-like motion. Here we depict the behavior of the Fourier power spectra for particles with different aspect ratio, but at different effective temperature, with the lowest constant magnetic field. Also, in this case, we observe most of the curve show a beta exponent near to value of 2. The same occur if the same phenomena, the same strength occur when we calculate the beta exponents for the rotational motion. In this case, we present the Fourier power spectra in the cases of different aspect ratio and different constant magnetic field. And in this last figure, we show the Fourier power spectra for different particle concentration and different constant magnetic field. As conclusion of all the studies we had carried out, the time series of the ellipsoidal particle position in the X direction and angular time series constructed from the rotational motion follows a power law with beta exponent near to value of 2, indicating Brownian-like motion. In the absence of a constant magnetic field, the scale invariance property is valid only for high values of the oscillating magnetic field. Thank you very much for your attention. Here are our mail address for further contact. Thanks again.